We're asked to evaluate this path integral. And even in the notation, it's like whoever wrote it is telling me that this must be path independent. I'm not going to take their word for it. This is a path integral through a vector field in its scalar differential form. So I want to make sure that the field we're dealing with is conservative before we get too far into it. And so I'm going to write that field down. And I have two options. If I can just find easily a potential function, a scalar function f, so that this is its gradient field, I'd be done, right? Because I know gradient fields are conservative and I know conservative fields are gradient fields. And I actually think if you pause the video here, you can find a potential function for this without thinking too hard. But I'm going to go through the component test anyway, because I just want to practice that skill. So I'm going to do the component test here, and then I'm going to find a potential function, and I'm going to evaluate this line integral in its scalar differential form just by using the fundamental theorem of line integrals. But I'll pause here and let you see if you can just think up a function f. Okay, I'm going to go through the component test for this vector field. So I need to test all three parts. So I need to compare the partial of m with respect to y to the partial of n with respect to x. I need to compare the partial of m with respect to z to the partial of p with respect to x. And finally, the partial of n with respect to z and the partial of p with respect to y. Okay, so I'm going to think about this as a 2x times x squared plus y squared plus z squared to the minus first. So the partial of m with respect to y, well, I get that minus 2x, take 1 away from the exponent. So that would now be a minus second, so on the bottom as a 2, times the derivative of y squared, that function on the inside, so I'd end up with a minus 4xy. Do the same thing, the partial of n with respect to x, and I do exactly the same calculation, right? I get exactly the same thing, except for now it's a derivative of x squared and a 2x on top. So like right away I see I'm going to get exactly the same thing. And you can go on and fill in the details here, but it's literally doing the same derivative 1, 2, 3, 4 more times, just taking the derivative of the correct piece on the bottom using the chain rule. So I'm going to say this does pass the component test, and of course if I was turning this in I would show all of my work and not just put a big check mark on it. But this is a conservative field, so I should be able to find a potential function for it. So thinking in that way, this is the partial of f with respect to x. So I want to think about finding an antiderivative of that with respect to x, treating y and z as if they were constants. And maybe you just thought of what the derivative was a moment ago. Antiderivative was a moment ago and already have your potential function. And that would be fine, but I'm going to imagine showing all of my work. Y and z are constants, so this substitution is going to be a very easy one, right? It's one of those nice ones where that's just all du, and I have a 1 over u du. And so, well, that's going to be the natural log of the absolute value of u plus some function that might vary on the variables y and z. All right, but u is x squared plus y squared plus z squared. In the presence of all of those squares, I don't need the absolute value. So my first candidate for my potential function is f of x, y, z equals the natural log of x squared plus y squared plus z squared. And I should write plus maybe some function g of y of z, but if I just imagine taking partial derivatives, well, if I take a partial with respect to y, I get 1 over x squared plus y squared plus z squared times 2y. Well, that checks out, and so does the partial with respect to z. So I'm just going to say I've found my potential function. All right, so what do we know now? Well, we did all of this work so that we could write down a potential function for that vector field. And that potential function was f of x, y, z is equal to the natural log of x squared plus y squared plus z squared. Well, now I can evaluate this path integral just using the fundamental theorem of line integrals. I need to know f of 2 comma 2 comma 3 and f of minus 1 comma minus 1 comma minus 1. Well, that's going to be 4 plus 4 is 8 plus 9. That's the natural log of 17. And here I have 1 plus 1 plus 1. Well, that'd be the natural log of 3. So I have the natural log of 17 minus the natural log of 3. And if I wanted to, through properties of the natural logarithm, I could write that as the natural log of 17 thirds.